NASA went looking on the dark side of the moon, and what they found blew up the old story of how the moon, and maybe even Earth, came to be. In this video, we're diving straight into what NASA really found on the dark side of the moon, and why they can't walk it back now. You've never seen half of your own moon, because the same face is turned toward you for your entire life. The moon does spin, but it spins once in about 27.3 days and orbits Earth in about the same time, so the same hemisphere is always facing you. That lock is called tidal locking. One side, the near side, is constantly turned toward Earth, the other side, the far side, is turned away. Both sides get day and night, but from Earth you are stuck looking at just one face. This is why the phrase dark side of the moon is misleading. The far side is not permanently dark, it spends about 2 weeks in sunlight and 2 weeks in darkness, just like the near side. When the near side is full and bright for you on Earth, the far side is actually in night, and when the near side is dark, the far side is in full daylight. So the issue is not that the far side is in shadow all the time, the issue is that your planet never lets you see it directly. So if one hemisphere is hidden from your eyes, how did NASA actually find out what is there? The first far side photos came in the 1960s, from early lunar orbiter spacecraft and other missions that looped around behind the moon. Those images showed a surface with many more craters and far fewer dark lava plains than the side you know. But the resolution was low, the positions of features were rough, and large areas were barely more than fuzzy shapes. You could tell the far side looked different, but you could not plan a precise landing or detailed geological study from those early photos. That changed with a modern spacecraft called the Lunar Reconnaissance Orbiter, or LRO. It flies in a polar orbit, passing over both poles on every lap, only about 50 kilometers, roughly 30 miles above the surface. On each orbit, its cameras scan long strips of ground. Over years, those strips were stitched into a mosaic that covers the entire moon, near side and far side under the same lighting with the same instruments. The far side stopped being a blank on a globe and became a mapped landscape point by point. The wide-angle camera on LRO built a global map at about 100 meters per pixel, so each pixel is a 100 by the 100 meter patch, about the size of a city block. In selected regions, its narrow-angle cameras go much finer, down to around half a meter, where you can pick out boulders as big as small cars or houses. LRO collected more than 15,000 separate images for the wide map alone. Every crater rim, every ridge, every patch of smooth ground on the far side now sits in a real dataset, not just an artist's guess. But high-resolution pictures only change the game if you can attach accurate coordinates to them, so what did that do in numbers? Before LRO, the positions of far-side features could be off by 2 to 3 kilometers, about 1 to 2 miles. That kind of error is huge. If you're trying to target a safe landing site near a particular crater or hill, you might aim for a flat floor and actually come down on a slope or a boulder field. With LRO and follow-up tracking, the locations of many surface features are now known to better than about 100 meters, around 328 feet. That shift from kilometer-scale uncertainty to 100-meter scale precision is the difference between somewhere in this general region and within a football field of that exact spot. For mission planners, that means you can choose a landing ellipse that avoids steep slopes, avoids big rocks, and still gets you close to the scientific targets you care about. For scientists, it means you can compare crater counts, rock types and heights on the near side and far side in a consistent way without wondering if your map is warped. Once the coordinates are solid, the key question is, what patterns jump out when you compare the two hemispheres side by side? The near side, the face you see from Earth, is dominated by large, dark basalt plains called maria. These are ancient lava seas, created when big impacts cracked the crust and let magma flood out, filling low basins. The far side, in contrast, has almost no large maria. It is made mostly of bright highlands crust, heavily cratered, higher on average and much rougher. Even a quick look at the global maps shows this split. One hemisphere with big dark circles and smoother areas, the other hemisphere bright and pitted almost everywhere. This is not a cosmetic detail, It tells you that the moon's interior did not behave the same way on both sides. On the near side, the crust was thin enough and the interior hot enough that magma could reach the surface repeatedly and resurface huge regions. On the far side, that kind of lava flooding was rare. The crust stayed thicker, the interior stayed cooler, and old craters stayed exposed instead of being buried. That raises a deeper question. Why is one side of a single small world built and resurfaced so differently from the other side? The answer is still being worked out, but one thing is clear: the far side preserved much more of the early history of the moon. Because it did not get wiped clean by large seas of lava, its surface is closer to the original battered crust that formed more than 4 billion years ago, holding a dense record of impacts. When NASA and other agencies mapped that far side at high resolution, with good topography and gravity data, they were opening that record for the first time. Every crater count, every elevation profile, every patch of undisturbed highland terrain on the far side feeds into models of how often big impacts happened, how fast they tailed off, and how the lunar crust responded. That also feeds into our picture of what was happening to Earth at the same time, because both worlds were being hit by the same population of objects. So the real impact of seeing the so-called dark side is not that anyone found aliens or ruins. It is that the far side forced us to drop the old idea of a simple uniform moon. A thicker, brighter, more cratered far side mapped in detail instead of guessed from a few blurry photos tells you the moon is fundamentally lopsided in its structure and its history. And that leads to a harder, more unsettling question that drives the rest of this story. If the far side holds the clearest record of ancient impacts and interior structure, what happens when you focus on the single biggest scar on that hidden hemisphere? A basin so large and deep that it pushes our models of lunar formation to the limit. How big does a crater have to be before it stops being just another feature and starts being the main thing on the entire moon? On the far side, there is one impact basin that crosses that line. The South Pole Aitken Basin, usually called SPA. It sits mostly on the hidden hemisphere, and it is huge even by planetary standards. Across, it runs about 2,500 to 2,600 kilometers. That's roughly 1,550 to 1,615 miles. If you laid it on Earth, you'd go from somewhere near New York, past the middle of the continent, and partway back again, and you would still be inside the same impact structure. This is not a normal crater. This is a basin that dominates an entire side of the moon. Depth-wise, it is just as extreme. The floor of SPA lies about 6 to 8 kilometers below the surrounding terrain, 4 to 5 miles. Earth's average ocean depth is around 4 kilometers, so if you could somehow fill that basin with water, you would have a sea deeper than the typical Pacific or Atlantic. And remember, this hole was not slowly carved. It was blasted out in seconds by a single impact from a body tens of kilometers across, hitting at many kilometers per second. So if the basin is that wide and that deep, what did it do to the moon's overall shape? That's where NASA's instruments come in. The Lunar Reconnaissance Orbiter carries a laser altimeter called LOLA. It fires pulses of laser light down to the surface, measures the return time, and turns that into precise height data. By sweeping the far side over and over, it built a detailed topographic map of SPA and its surroundings. Those measurements show a vertical range that is hard to grasp at first. From the deepest point inside the basin to the highest peaks on its rim, the elevation difference is over 15 kilometers, about 9 miles. Mount Everest, the tallest mountain on Earth above sea level, is just under 9 kilometers tall, so the step from the bottom of SPA to its tallest rim peaks is close to stacking 2 Everests, one on top of another. All of that relief comes from one ancient impact event and the way the crust and mantle responded afterward. That kind of height difference tells you the crust did not just crack, it was pushed down, bounced back, and then frozen in place. You can see central rings, inner basins, and uplifted blocks in the topography data, all locked into the far side like a paused shockwave. The moon has no plate tectonics, no strong erosion, So once that shape formed, it stayed. SPA is basically the moon's biggest scar left open, still readable. The next question is timing. When did this hit actually happen? Scientists do not have samples directly from the basin floor yet, but they can date minerals and melts that are linked to it in Apollo samples and lunar meteorites. Radiometric dating, counting the decay of radioactive elements inside those grains, points to an age of about 4.2 to 4.34 billion years. That places SPA right in the era when the early solar system was brutally violent, when leftover planetary building blocks were still on unstable orbits and were slamming into the inner worlds. So when you look at this single basin on the far side map, you are not just looking at local geology, you are looking at one of the oldest identified impact structures in the entire solar system. That impact would have shaken the whole moon, and the energy involved was in the same league as the biggest hits that shaped Mercury, Mars, maybe even early Earth. SPA is a direct data point about how intense that era really was. If an impact is old, giant and deep, the obvious question is, how far down did it dig, and what did it bring up? The answer is probably very deep. Models of large impacts combined with the moon's gravity and topography data suggest that SPA excavated material from the lower crust and maybe even from the upper mantle. In other words, it did not just scrape the surface, it punched through a big fraction of the moon's outer shell. Missions like GRAIL mapped the moon's gravity field and found that the crust inside SPA is thinner than average, and the basin floor sits lower than expected if it were just filled with normal crustal rock. That lines up with the idea that denser, deeper material was lifted closer to the surface there. In simple terms, SPA is like a natural borehole. Instead of drilling 15 kilometers down with machines, something hit the moon once at maybe 10 or 20 kilometers per second and did the excavation for you. For future missions, that changes the value of the site completely. If you land near the basin interior or on parts of its rim, the rocks you pick up are not just random surface dust. They might be pieces of the lower crust or upper mantle that would normally be totally unreachable. For programs like Artemis, that makes SPA a prime target for sample return. Each kilogram of rock you bring back from there could carry information about the deep interior, not only about the top layers. So then you get to the real strategic question: why could this one basin end up deciding where humans go next on the moon? The answer is about leverage. Because SPA is so old and so deep, its rocks are some of the best tests you can get for moon formation theories. If you think the moon formed from a giant impact with early Earth, and then crystallized from a global magma ocean, that process should leave specific chemical and isotopic fingerprints in the deep crust and mantle. A single well-chosen sample from SPA's interior or rim could match those predictions, or completely contradict them. It could show that the lower crust has the expected mix of elements, or that it is radically different. It could confirm that certain heat-producing elements really did concentrate on one side, or say, no, that picture is wrong. Because of that, far-side landing concepts from NASA and other space agencies tend to cluster around SPA's rim and nearby highlands. If you want to know how violent the early inner solar system really was, and how that violence built the moon you see today, you do not just land anywhere. You go stand on the edge of the biggest scar, and you pick up the oldest, deepest rocks you can reach. That is the appeal of SPA, and also the pressure. It is not just another cool crater. It is a location where one mission could either support decades of models, or force everyone to throw them out. And that leads straight into the next tension point. If the surface shape and depth of this basin tell you about one huge impact, what do you find when you stop looking at the surface at all and instead map the moon only through its gravity, seeing how mass is actually distributed under both the near side and the far side? So how do you study the side of the moon you can't see inside, not just the surface, but the hidden mass underneath? Pictures will not help you there, you need gravity. That is why NASA launched the twin GRAIL spacecraft, nicknamed Ebb and Flow. They did not carry big cameras for pretty images, they carried radios and precise navigation. Here is the basic idea. Put two small spacecraft in the same low orbit around the moon, one following the other. As they fly over mountains, basins, and dense patches underground, the gravity changes slightly. The leading spacecraft speeds up or slows down by tiny amounts, millimeters per second. The trailing spacecraft feels those changes at slightly different times. By tracking the distance between the two with radio signals, you can see those tiny stretches and squeezes in the formation. Those tiny changes in distance, sometimes only a few micrometers, get turned into a 3D gravity map. Stronger gravity means more mass underneath. Weaker gravity means less mass. Do this over and over for months at different angles, and you build the most precise gravity map ever made for any body beyond Earth. GRAIL turned the moon from a surface-only world into one where you can actually see indirectly how the mass is arranged inside. Once you have that map, the next question is simple and brutal. Does the far side feel the same on the inside as the near side? The answer from GRAIL is no. When scientists combined the gravity data with topography maps from LRO, they could solve for how thick the crust is in different regions. The result is a genuine split personality. On the near side, the crust thickness tends to be around 30 to 40 kilometers. On the far side, the average is about 20 kilometers thicker. So you're looking at many areas with 50 to 60 kilometers of crust, a solid extra layer of rock. If you want an intuitive picture, think of taking an already thick slab of continental crust, then placing another Manhattan-sized block of rock on top of it everywhere across a hemisphere. That is roughly what the far side did compared to the near side. That extra 20 kilometers is not a small difference at planetary scale. It fundamentally changes how easily magma from the mantle can reach the surface. Thin crust is easier to crack, easier to punch through, and more likely to let lava flood out when big impacts happen. Thick crust is harder and colder. It takes far more energy to open a path, and many magma pockets will stall and cool down before they ever erupt. This leads straight into the next question you care about. Why did the near side get huge seas of lava, the Maria, while the far side mostly did not? GRAIL's crust thickness result is a major piece of that answer. On the near side, you have relatively thin crust plus extra internal heat from radioactive elements concentrated there, especially in the region called the Procellarum Creep terrain. When large impacts hit those basins, the cracks went deep, magma rose, and there was enough heat to keep it molten until it could spread out across the surface. On the far side, the story is different. The crust is thicker by those extra tens of kilometers, and the heat-producing elements are less concentrated. That combination means the mantle under the far side is cooler, less melted, and even when it does melt, it has to fight through more rock to get out. Most of it never makes it. The result, when you look at NASA's high-resolution maps, is almost pure highlands on the far side, dense with craters, almost no large, dark lava seas. So the lack of Maria on the far side is not just bad luck or fewer impacts. It is a physical consequence of thicker, colder crust. The far side had fewer chances for big, sustained lava floods. When you flip the moon over in your head, from the near side you know to the far side you never see, you're really flipping from a crust that could bleed lava easily to a crust that stayed locked up. But gravity does not just tell you about average crust thickness, it also shows you where mass is strangely concentrated. That is where another piece of the GRAIL story comes in, mascons, short for mass concentrations. Under many of the large impact basins, especially the circular Maria, gravity is stronger than you would expect just from the visible topography. Something dense deep down is adding extra pull. These mascons were not a new idea. Apollo and earlier orbiters had already noticed them the hard way. Spacecraft flying low over certain basins would see their orbits drift off, as if something heavy underground was tugging on them. Controllers had to add extra corrections to keep trajectories on track. GRAIL took that rough practical knowledge and turned it into a detailed map. Here is the catch. When you compare near-side and far-side mascons, the patterns are not the same. Near-side basins often have strong centralized mascons, where dense mantle material has risen under a lava-filled basin. Far-side basins also have gravity anomalies, but their shapes and strengths differ. often weaker or more spread out. That suggests the mantle under the far side did not flow and rebound in the same way after big impacts. Again, you are seeing a deeper asymmetry, not just a surface difference. This is where the stakes really ramp up, because once you accept that the moon's interior is lopsided, you cannot keep the old simple origin story. A thicker, cooler far side, plus a thinner, warmer near side, plus different mascon patterns, all point to some huge early asymmetry in how the moon formed and cooled. One class of ideas says the original giant impact that made the moon was slightly off-centre, leaving more hot, mixed material on the near side and thicker, stiffer crust on the far side. Another idea says there may have been a smaller companion moon that later collided slowly with the bigger one, plastering extra crust onto one hemisphere. Whatever the exact mechanism, missions like GRAIL turned the far side from just more craters into hard evidence that the moon is geologically one-sided. Any serious model now has to explain why heat-producing elements pooled where they did, why the crust thickened on one side, why lava erupted mostly on the other, and why the gravity field looks so different between hemispheres. The far side is no longer just the hidden half, it is the control case that proves the moon's interior story is more complicated and more violent than we thought. And that pushes you to the next uncomfortable question. If the far side's deep structure is this different, what else is missing there that you expect to see? And why did whole categories of volcanic activity almost never break through on that side at all? You turn the mapped globe of the moon around and something basic suddenly goes missing. Where did all the dark seas go? On the side that faces Earth, those dark mare plains cover about 31% of the surface. Flip to the far side and the true Maria shrink to roughly 1%, just a few scattered patches inside big craters. This is not a drawing trick or a colour choice, it's a hard geologic signal. One hemisphere is heavily resurfaced by lava, the other is almost completely left in bright ancient crust. That mismatch forces a basic question. If the whole moon formed from the same stuff at the same time, why did only one side get massive lava floods? The old lazy answer was, maybe the near side just had more big impacts, so more basins filled with basalt. But the more we've mapped both hemispheres, and the more we've counted craters and basins, the less that answer fits. Both sides got heavily bombarded. The difference is not how often things hit, it's how the interior responded when they did. So you go back to the GRAIL gravity data and the LRO maps, and you ask, what is physically different on the inside? One big piece you already saw, the crust on the far side is, on average, about 20 kilometers thicker than the crust on the near side, which tends to be around 30 to 40 kilometers in many regions. That extra 20 kilometers of rock is not subtle, it is a barrier. Magma rising from the mantle has more distance to travel, more pressure to fight, and more time to cool and solidify before it ever reaches the surface. But thickness is only half the story, the other half is heat. Inside a rocky body, long-lived radioactive elements like uranium, thorium, and potassium act like tiny built-in heaters. When they decay, they release energy and keep the surrounding rock hotter for longer. Gamma-ray maps and geochemical work show that these heat-producing elements are heavily concentrated on the near side, especially in a region called the Procellarum Creep Terrain. That area covers a modest fraction of the moon's surface, but seems to hold a big chunk of its radioactive budget. Put those facts together, and you get a simple harsh rule. The near side has thinner crust and more internal heating, the far side has thicker crust and less internal heating. A cooler mantle plus a thicker lid is basically a volcano kill switch. On the near side, big impacts can crack the crust, tap into hot, partially molten mantle, and let huge volumes of basalt erupt to form the Maria. On the far side most of the time, the same kind of impact will just make a crater, and maybe some local melt, but it will not open a long-lived path for deep magma to drain out. All of this was a strong theoretical picture from orbital data, but until recently it was still missing one key piece, a physical rock from the far side interior to test the temperature story directly. That gap finally closed with China's Chang'e 6 mission in 2024, which landed in the South Pole Aitken region on the far side, and brought back about 2 kilograms of samples. Lab work on those rocks shows they'd crystallized from lava roughly 2.8 billion years ago, and the chemistry lets scientists estimate the temperature of the source magma. Those estimates cluster around 1,100 degrees Celsius, about 2,000 degrees Fahrenheit, which is roughly 100 degrees Celsius, about 180 degrees Fahrenheit, cooler than comparable basalt sources on the near side. That is not a tiny difference. For mantle rocks, hotspots, 100 degrees can be the line between partially molten and mobile and mostly solid and stuck. The Chang'e 6 result lines up with what NASA's gravity and spectral data were already telling you. The far side mantle really does run colder. So now you have 3 independent threads that all say the same thing. GRAIL showing a thicker, far side crust, gamma ray and composition maps showing less thorium and other heat sources on that side. And direct far side samples showing cooler source lavas. Taken together, they kill the old idea that the moon's interior is basically symmetric, and the surface differences are just impact statistics. The far side is not just more unlucky with craters or less lucky with lava, it is genuinely built and cooled differently. For decades, many models worked with a simple picture: one global magma ocean, one crust thickness profile with small variations, same basic mantle on both hemispheres, and then impacts and time do the rest. The combined near side and far side data say no. The near side has extra heat producing elements, more extensive basalt flooding, a different gravity pattern, and evidence of a warmer interior. The far side has thicker crust, fewer heat sources, cooler mantle temperatures, and very limited volcanism. The moon is not one uniform story, it is 2 overlapping ones. That has direct consequences for how you think the moon formed. Any serious origin model now has to explain why those heat-producing elements ended up pooled mostly on one hemisphere, why the crust thickened more on the other, and why the deep mantle under the far side stayed cooler over billions of years. Maybe the original giant impact was off-center. Maybe material rich in radioactive elements migrated toward the side facing Earth. Maybe an early smaller moon merged in a way that stacked extra crust onto one half. Whatever the detailed answer, one giant impact and everything mixes evenly is no longer good enough. And this is not just an academic problem for modelers, it hits real mission planning. If you are designing Artemis-era landers, drills and habitats, a cooler, thicker crust on the far side changes your engineering. To reach certain depths, you need more power and stronger bits. To deploy heat flow probes that measure how much energy is leaking out of the interior, you have to account for the fact that the far side will give you a different signal than the near side. For mining, thicker, colder rock means slower progress and different equipment wear. A simple way to picture the challenge is this: the material is broadly the same, but the conditions are not. It is like comparing trying to melt through thick Arctic sea ice versus thin lake ice. Both are frozen water, but one demands more energy, more time and more robust tools. On the moon, the far side is that tougher case. You get access to pristine highlands and deep time records, but you pay for it with harder drilling, colder subsurface conditions, and more demanding logistics. So you are left with a far side that is almost a volcanic desert, a hemisphere where large lava seas barely exist, even though giant impact basins and deep crustal holes are present. That sets up an obvious tension for the next part of the story. If the far side is supposed to be mostly shut down volcanically, what does it mean when one small region there lights up in the data as a concentrated, strange volcanic complex that looks like it belongs on the more active near side, not in this off hemisphere? On a hemisphere that is supposed to be cold, thick, and basically done with volcanism, what do you do when one small patch looks like it never got the memo? On the far side, buried in a field of old highland craters, there is a single odd zone called the Compton-Belkovich volcanic complex. It sits between the craters Compton and Belkovich, and it's only about 25 to 35 kilometers across, roughly 15 to 20 miles. In global terms, that is tiny, but in compositional terms it stands out hard. The rocks there are enriched in thorium and other elements linked to unusual magmas. totally unlike the typical basalt flows that built the Dark Maria on the near side. On a far side that should be mostly ancient crust and impact scars, this region behaves like a leftover volcanic hotspot. So how did anyone even notice this small patch on a whole hemisphere covered in craters? The first clue came in the late 1990s from NASA's Lunar Prospector mission. It carried a gamma-ray spectrometer, an instrument that measures high-energy photons coming off the surface. Different elements produce different gamma-ray signatures, and one of the key targets was thorium, a heat-producing radioactive element. As Lunar Prospector circled the Moon, it built up a global map of thorium abundance. On most of the far side, thorium levels looked low, which fits the cooler, thicker crust story you already saw from gravity and chemistry. But in one spot near Compton and Belkovich, the data showed a clear spike, a thorium anomaly. That excess thorium suggested that the rocks there had a very different history, with magmas that had been concentrated and evolved, not just simple runny basalt. On Earth, that kind of geochemical signature points to long-lived magma systems and more complex volcanic products, not just plain lava floods. Once that anomaly was on the map, it became a target. Follow-up observations with the cameras on the Lunar Reconnaissance Orbiter showed a cluster of bright, irregular domes and mounds, not shaped like typical impact features. The area has a different texture and reflectivity than the surrounding highlands. LRO Diviner, the infrared radiometer on LRO, added another piece. The thermal behaviour of the ground there is different. It cools at night in a way that matches a distinct rock type, not just ordinary crust. Put together, the thorium spike, the brightness, the morphology, and the thermal data say the same thing. This is a real volcanic complex, not just a random bright patch or a weirdly lit crater. The obvious next question is, what kind of volcanism is this? Most of the Moon's known lavas are basaltic, low in silica, relatively fluid, similar to what you see in places like Hawaii. The Compton-Belkovich region does not fit that. Spectral data from orbit indicate these rocks are richer in silica, more like rhyolite or dacite on Earth. That is called silicic volcanism. Silicic magmas are thicker, trap more gases, and usually require more time and more processing in the crust to form. They are associated with long-lived magma chambers and significant crustal melting. On Earth, you usually find silicic volcanic centres in areas with thick crust and strong heat flow, like continental arcs or big volcanic provinces. On the Moon, almost all previously known silicic features sit on the near side in or near the Procellarum creep terrain, which is rich in potassium, rare earth elements and phosphorus, plus uranium and thorium. That region was already flagged as the Moon's geochemical odd zone. The Compton-Belkovich complex, however, is roughly 900 kilometers away from that terrain on the far side, inside highlands that should be colder and more chemically simple. That distance matters. If all strange silica-rich volcanism lived on the near side's creep-rich terrain, you could argue that the weirdness is all local. But Compton-Belkovich breaks that pattern. It says that even on the far side in supposedly simple thick crust, there were places where enough heat and enough chemical separation existed to build evolved, silicic magmas. That means the far side interior was not uniformly cold and boring. It had pockets of complexity. Then you have the timing question, how old is this thing? Most big basalt flows on the Moon date back 3 to 4 billion years. They belong to an era when the interior was still relatively warm and impacts were still frequent and violent. Crater counts and thermal modelling for Compton-Belkovich suggest something different. Some studies point to ages that could be as young as around 1 billion years, though there is a range of estimates. Even taking the uncertainties seriously, this pushes it significantly younger than the bulk of lunar volcanism. If that younger end is close to the truth, it means this far-side hotspot could have been active, or at least warm, at a time when life on Earth already had multicellular forms in the oceans. While Earth was moving toward complex ecosystems, the dead hemisphere of the Moon might still have been quietly producing exotic, silica-rich lavas in one isolated region. That picture is not what you expect from a small world that is supposed to cool quickly and shut down deep activity early. So what does one stubborn volcanic complex do to the bigger moon story? It forces you to admit the interior is not just asymmetric between near side and far side, it is also patchy and messy inside each hemisphere. Compton Belkovich says that even under thick colder crust, the far side could trap heat and melt pockets of rock enough to drive unusual volcanism, long after the main phase of mare formation ended. It acts like a warning label on the whole simple moon narrative. For future missions, this region also becomes a high-value target. A sample returned from Compton Belkovich would give you direct constraints on the age of the eruptions, the composition of the silica-rich magma, and the amount of heat-producing elements concentrated there. That would tighten our models of how long volcanism lasted on the far side, how local or global the weird chemistry really is, and how efficient the moon was at moving heat around in its crust and mantle. For you, watching from Earth, the key point is blunt. On a hemisphere that is supposed to be geologically quiet, Compton Belkovich is a clear sign that the interior stayed more complicated and more active, for longer than the old models allowed. It is one blinking hotspot on a dead side, telling you that the moon's engine did not shut off evenly, and that far-side rocks can still surprise you badly. And if a single patch of rock can violate the rules this much, it sets up an even sharper problem. What happens when you stop looking only at surface geology and chemistry and start following the invisible pull of gravity itself, into regions where spacecraft paths bend in ways that make it look like they're falling toward hidden mountains under the ground? How do you know there are hidden lumps of mass under the surface if you can't see them and you can't dig down to touch them? The first hints came from something very practical: spacecraft navigation. During the Apollo era and even earlier with Lunar Orbiter, mission teams noticed that over certain regions of the moon, the spacecraft orbits dipped and drifted in strange ways. It was like the spacecraft was suddenly falling uphill, speeding up toward invisible mountains that weren't there in the topography. The only way that makes sense is if there are mass concentrations, mascons, buried under the surface, mostly under big impact basins. The extra mass pulls a spacecraft a little harder as it flies overhead. Before precise gravity maps, teams had to discover these the hard way, by seeing their predicted orbits slowly go wrong, then patching in extra corrections. It worked, but it was like flying through turbulence you can't see on the weather radar. Once GRAIL showed up, that guesswork ended. By tracking the tiny distance changes between the twin spacecraft, scientists could map whether gravity was stronger or weaker with very high precision. Suddenly, those old spooky regions weren't just places where the orbit misbehaves, they were detailed gravity anomalies. On the near side, many circular basins lined up with strong central mascons. On the far side, there were still mascons, but their patterns and strengths were different, often weaker, sometimes offset, sometimes spread out. So the question becomes, why do impact basins on one hemisphere have different gravity signatures than basins of similar size on the other hemisphere? To answer that, you have to think about what a huge impact actually does to a planet's crust and mantle. When something big hits at high speed, it doesn't just dig a hole, it sends shockwaves through the rock, pushes material down, lets it rebound, and can make mantle material well up. The crust and mantle literally oscillate, like a bell that's been struck. On Earth, erosion, plate tectonics, and ongoing geology erase most of that long-term structural memory. The surface might keep a crater, but the deep density structure evolves. On the Moon, there is no plate tectonics, no oceans, and almost no atmosphere. Once the crust and mantle finish bouncing and flowing after an impact, the final mass distribution mostly freezes in place. The gravity field remembers what happened, even after the surface has been micrometeorite sandblasted for billions of years. GRAIL's data show that near-side basins tend to have strong compact mascons, consistent with dense mantle material rising under a basin that later filled with heavy basalt. The far side doesn't play by that same rule. Many far-side basins have weaker mascons, or more irregular ones. Some don't show the same kind of dense central plug you see under the big near-side Maria. That points back to the thicker crust and cooler mantle you already heard about. The far-side crust and mantle did not bounce and flow the same way after impacts. They relax differently, and that difference is still written into the gravity. Then comes the very practical question, why should you care about this if you're focused on future missions, not on old impacts? Because if you are flying a spacecraft low over the surface, gravity is not a background detail. It is the thing that decides where you actually end up. Take a lander coming in at about 1.7 kilometers per second, around 3,800 miles per hour, on final approach to the far side or the poles. If your gravity model is off by even 0.1% in that region, your trajectory can drift by kilometers. That kind of error is the difference between touching down near your carefully chosen science site and slamming into a hillside you thought was 5 kilometers away. For orbiters skimming low to map ice or temperature, a bad gravity model can shorten mission life because you have to burn more fuel correcting your path. So when GRAIL hands you a detailed gravity map, with mascons and subtle variations laid out, it's not just a nice-to-have scientific product. It's the baseline for safe navigation around the far side and in complex polar orbits. And the far side is exactly where a lot of future interest lies, both for science and for things like radio-quiet observatories. That means you need confidence that hidden lumps of mass are not going to quietly sabotage your path. With the GRAIL maps, agencies can plan trajectories and landing profiles that already account for those invisible mountains of mass underground, instead of discovering them mid-mission the way Apollo did. All of that brings you to the bigger point. What does this say about the Moon as a whole? The key idea is that gravity is not just about pulling spacecraft around, it is a fossil record. The mass distribution you see today is the end result of impacts, crust formation, mantle flow, and cooling over billions of years. When you see strong mascons under certain basins and weak or oddly shaped mascons under others, you're looking at frozen snapshots of how the interior behaved when it was still hot enough to move. On the far side, that gravity fingerprint is loud and consistent with everything else you've heard. The crust is thicker, the mantle is cooler. The big impacts did not drive the same kind of dense upwelling and basalt flooding that they did on the near side. The mascon patterns reinforce the crust thickness story from GRAIL, and the missing Maria story from the surface maps. All three lines of evidence say the same thing. The far side's interior followed a different cooling history. So now you have a far side that's structurally thicker, volcanically poorer, yet still hiding complex hotspots and subtle gravity structures. That naturally leads to the next uncomfortable question. If the far side is this strange in its rock and its gravity, what happens when you stop thinking about rocks at all and ask what happens to radio waves and electromagnetic noise on the hidden side of a world that blocks Earth's entire broadcast chatter? Radio noise is everywhere around you, but there is one place nearby where it almost completely dies, the far side of the Moon. If you want to listen to the universe at ultra-low radio frequencies, below about 30 to 50 megahertz, Earth is basically useless. Earth's ionosphere bends and blocks those long wavelength signals, and what does get through is buried under a mess of human radio noise from power lines, phones, radar, FM, TV, satellites, everything. Even if you go to a remote desert on Earth, you are still sitting under a buzzing shell of interference. Now take that whole noisy planet, put the Moon between you and it, and stand on the hidden hemisphere. The rock of the Moon, thousands of kilometers thick, blocks and absorbs most of those radio waves. Simulations and measurements from orbit show that on the far side, the strength of Earth-generated radio signals drops dramatically. From the point of view of a radio antenna on that side, Earth's chatter is heavily muted. It's not perfect silence, but compared to the radio chaos you live in, it's the quietest place in the inner solar system. So what does that buy you in real science terms? Why are NASA scientists and radio astronomers so fixated on this quiet zone? Because the cosmic signals you care about at those low frequencies are incredibly faint. One of the big targets is the 21 centimeter line from neutral hydrogen, stretched by the expansion of the universe to very long wavelengths. At high redshift, from the era before the first stars and galaxies, that line slides down into the range below 50 megahertz. That time period is called the Cosmic Dark Ages. There were no stars yet, no galaxies, just neutral hydrogen slowly cooling and clumping under gravity, while the cosmic microwave background glowed in the background. The only way to study that era directly is through low-frequency radio waves. If you can map how that hydrogen was distributed, you get a direct picture of how structure started to form long before galaxies appeared. From Earth's surface, you simply cannot reach those frequencies cleanly. The ionosphere blocks them or distorts them, and the remaining band is full of man-made interference. You can put radio telescopes in space, but a single spacecraft is small and has limited collecting area. The far side of the Moon offers something different, a giant stable shield that blocks Earth's noise and provides a solid surface where you can spread out antennas over many kilometers. That is why you see so many papers and mission concepts calling the lunar far side the best place in the solar system for low-frequency radio astronomy. A big dipole antenna array there could listen directly to the Dark Ages signal, something we have never measured. For cosmologists, that is a high-value prize, on the same level as the first detailed maps of the cosmic microwave background were in the 1990s and 2000s. But there is a hard engineering reality sitting under that dream. To pick up these faint signals, you do not just need one antenna, you need thousands. Picture simple dipole antennas spread out over tens of square kilometers, maybe an area comparable to a small town. Each antenna is light and basic, but the array as a whole is huge. You have to lay power lines or solar units, data links, central processing units, and you have to keep all of it synchronized to very precise timing. On top of that, your tolerance for local interference is almost zero. A single poorly shielded transmitter, a rover with a noisy electronics package, or a lander that keeps pinging home on the wrong frequency can ruin the data for a large part of the array. This is not like building a radio telescope next to a quiet city where you can just make some zoning rules. You need a whole region to stay radio clean, down to very low power levels, all the time. That is why scientists are already pushing for something that sounds unusual for the Moon: legal protection of specific far-side sites. They want some craters or plateaus designated as radio quiet zones, where future missions are strictly controlled in terms of transmitters, frequencies and operations. The concern is simple: if we start dropping landers, relay satellites, mining rigs, and surface bases everywhere without planning, we could permanently contaminate the very quiet zone we need for this science. This leads to a serious fork in the road for exploration. On one path, the far side becomes the ultimate observatory. We deliberately keep a core region clean, we land carefully designed radio missions, we deploy kilometre-scale arrays, and we finally listen to those earliest hydrogen signals that would let us watch the universe transition from a dark, simple state to the first flickers of starlight using a radio ear protected by the Moon itself. On the other path, we treat the far side as just another patch of real estate. We put relay satellites in noisy orbits, we park landers with strong transmitters in the wrong places, we run surface operations that leak radio noise into low frequencies. By the time we are ready to build a serious Dark Ages array, the environment is already polluted enough that the whole advantage is gone. The quietest place in the inner solar system turns into just another noisy zone, and that window into the early universe stays mostly closed. So the stakes here are not just scientific, they are about timing and priorities. The same hidden hemisphere that already forced us to rewrite the Moon's geological story now offers our best shot at seeing back into the time before any stars existed. The question is whether we have the discipline to protect that radio silence long enough to use it properly, or whether we burn it without thinking in the rush to build anything anywhere as fast as possible. And that connects directly to the next layer of the far side story, because the quietest radio zones and the most sensitive science sites often sit near the poles, close to regions of permanent shadow that may hold something very different but equally valuable: ancient ice, locked in darkness at temperatures colder than Pluto. How cold does it have to get before normal materials start behaving more like they are in a lab experiment than on a world surface? Near the lunar poles, some crater floors never see sunlight at all, and that pushes the temperature into an extreme range. The Moon's spin axis is tilted only about 1.5 degrees, very small compared to Earth's 23.5 degrees, so sunlight just grazes the polar regions. Deep crater rims catch the light, but the floors stay in permanent shadow. These are the permanently shadowed regions, PSRs, and they are some of the coldest known places in the inner solar system. NASA's Lunar Reconnaissance Orbiter carries an instrument called Diviner, which measures infrared radiation and turns that into a surface temperature. When Diviner looked into those PSRs, it measured temperatures below about 110 Kelvin, that's roughly minus 163 degrees Celsius, minus 261 Fahrenheit. Some modelled spots, especially in very deep traps, go much lower, toward 30 Kelvin, about minus 243 Celsius, minus 406 Fahrenheit, colder than the average surface temperature of Pluto. At those temperatures, almost every common volatile, including water, behaves like rock. It just sits there, barely moving. Those conditions immediately raise a key question. If these places are that cold, have they been quietly storing ice for billions of years? Micrometeoroids, comets, and the solar wind can all deliver water and other volatiles to the moon. In sunlit regions, that material gets broken down, heated, and lost to space. But in PSRs, once a molecule of water settles into the dark, it can stay there on geologic timescales. The polar craters start to look less like simple holes and more like cold traps, long-term freezers for whatever lands inside and can migrate down slope. To test whether that idea was real, not just a model, NASA flew a mission that did something very direct and a bit brutal. It hit one of those dark craters hard and watched what flew out. The mission was El Tiros. The setup was simple. The upper stage of a rocket, about 2 tons, was sent on a collision course with the south polar crater Cabeus, while a trailing spacecraft followed behind along the same path. The impact speed was about 9,000 km per hour, roughly 5,600 miles per hour. When that spent rocket stage slammed into the dark crater floor, it excavated on the order of 350 metric tons of material and carved out a small new crater about 20 meters across, around 66 feet. The trailing spacecraft flew through the ejector plume, watching with cameras and spectrometers as sunlight lit up the debris. In that plume, the instruments detected clear signatures of water, roughly 155 kilograms of it, about 340 pounds, similar to the total water mass of a couple of adult humans. For a small sample of one crater floor, that is a strong signal. El Tiros was a proof of concept. It showed that at least some PSRs hold real detectable water ice in the regolith, not just trace chemistry. After that, orbital missions pushed the picture further. Spectral data from instruments like the Moon Mineralogy Mapper on India's Chandrayaan-1, combined with LRO data, found direct signs of H2O ice at the poles in multiple PSRs. The spectra show features that match surface-exposed ice grains, mixed into the top layer of soil, sitting in locations that sunlight never reaches. That distinction matters. The Moon has widespread hydroxyl, OH, that can form transiently on sunlit surfaces as the solar wind hits oxygen in the regolith. But that is different from stable crystalline water ice sitting in the dark. The polar PSR detections point to actual ice deposits, not just fleeting chemical bonds. They're patchy, not thick glaciers, but they are real, and they've been sitting there mostly unchanged for a very long time. Now connect this back to the far side. Many of the most promising PSRs, especially near the South Pole, spill over into terrain that is partly or mostly on the far side, out of direct line of sight from Earth. Some candidate Artemis landing zones sit near the boundary, where you can still get radio contact over the limb while having access to PSRs that extend farther into far-side territory. These regions are high-value targets in 2 different ways at once. On the science side, each PSR is a sample of the solar system's delivery process. The ice there likely comes from multiple sources: comets, icy asteroids, the solar wind, maybe even outflow from Earth's upper atmosphere over billions of years. By drilling cores and analysing the layers, you can track how the flux of water-bearing material changed over time, how often comets hit, how the solar wind evolved, and how much material Earth has been losing. A PSR on the far side, shielded from some Earth effects, might preserve a slightly different record than one on the near side, giving you a way to separate local influences from more general ones. On the exploration side, the stakes are very practical. Water is not just something you drink. You can split it into hydrogen and oxygen for rocket fuel, use the oxygen for breathing, and use the water itself for cooling systems and radiation shielding. Every kilogram of water you can source on the moon is a kilogram you don't have to launch out of Earth's gravity well. That translates into cheaper missions, larger payloads, and more ambitious operations. If you can reliably mine and process ice in PSRs near the far side, fill tanks on the surface, and maybe set up a depot in lunar orbit, the whole architecture of deep space travel changes. The dark side suddenly stops being just a mysterious hidden hemisphere and becomes part of a supply chain. You launch dry hardware from Earth, refuel in lunar space with moon-derived propellant, and head outward with much more mass devoted to useful hardware instead of fuel. That is why people talk about these cold traps as a kind of future gas station, even though the analogy is rough. The coldest, darkest places on and just beyond the far side, the pits that never see the sun, may be exactly where future astronauts refuel landers, top up life support systems, and stage missions to Mars and beyond. The areas that pop out on LRO's temperature maps as colder than Pluto might end up being the backbone of an interplanetary infrastructure. And that leads straight to the next tension point. Once you know ice is there in the shadows, the obvious next question is, how much water is moving around outside those deep freeze zones? Where is it hiding in sunlit areas? And how does it migrate across a surface that looks dry and dead but keeps hinting that it isn't? You just heard that the darkest craters can hold ice. So the natural follow-up is, what about the rest of the moon? Is everything outside those shadows really dry? In 2020, NASA's airborne observatory SOFIA, basically a telescope in modified Boeing 747, gave a very direct answer, no. It detected water in sunlit regions like Clavius Crater, one of the big features you can see from Earth. The concentration was on the order of a few hundred parts per million, roughly like having a 350 milliliter bottle, a 12-ounce bottle, of water mixed into each cubic meter of soil. That amount is not a puddle. You can't scoop up a shovel of regolith and watch liquid drip out of it, but it is definitely not zero. And because SOFIA was measuring at a wavelength that distinguishes actual H2O from hydroxyl, it told you this really is water, not just a loose OH group bonded in a way that changes easily. The key point is, even where the sun shines, the moon's surface, including the far side, carries a measurable budget of water molecules. Once you know there is water outside the deep traps, the next question is, how static is it? Is that water frozen in place or is it moving? In 2023, scientists combined multiple SOFIA observations into a map that shows how the water signal changes with latitude, time of day, and surface type. The signal is stronger in some regions, weaker in others, and it varies as the surface heats up and cools down. That pattern hints at a cycle where individual molecules hop around the surface. Here's the basic idea. A water molecule sitting on a sunlit grain can get enough energy from heating or radiation to break free, jump into a ballistic trajectory and land somewhere else, maybe closer to a cold region. Over many hops, some fraction of these molecules find their way into colder traps, like shaded slopes or PSRs, and stay there longer. As the surface environment changes, some can be re-released. You end up with a thin, slow-motion migration of water across what looks like a dry, airless world. Because the far side has different topography and temperature patterns compared to the near side, it probably guides that migration differently. Highlands, deeper basins, and shadowed niches are arranged in another configuration. The far side might be better at capturing migrating water in some latitudes, or worse in others. That's one reason scientists don't just want a global average. They want detailed, location-specific maps that include both hemispheres. To push past broad hints and into detailed diagnostics, NASA is flying a dedicated water hunter orbiter, Lunar Trailblazer. It's a relatively small spacecraft, about 200 kilograms, roughly the mass of a big motorcycle. Instead of carrying a lot of different instruments, It focuses on high-resolution spectroscopy of water and hydroxyl and thermal measurements. It orbits low, around 100 kilometers, about 60 miles above the surface. Trailblazer's job is to answer three linked questions. First, where is water locked in as ice, especially near PSRs and polar regions? Second, where is water or hydroxyl bound inside minerals chemically integrated into the rock? Third, where is water more mobile, sitting on grain surfaces or moving in response to sunlight and local temperature? By mapping these states and their changes, Trailblazer can show you which areas act as long-term storage and which act more like transit zones. For future missions, that level of detail matters. If you're planning to harvest water, you want to know whether you're targeting stable ice mixed into regolith, hydrated minerals that will need more energy to process, or transient surface films that are too thin to be practical. For science, the same maps tell you how effective different latitudes and terrains are at trapping water over billions of years, and how quickly molecules cycle between free and stored states. The bigger shift here is in how you think about the moon itself. For a long time, the standard picture was a dry, inert rock, with maybe a bit of polar ice as a curiosity. Now, between LCROSS, LRO, Sophia, and missions like Lunar Trailblazer, the story is different. Water is being delivered, moved, trapped, and sometimes lost. It responds to sunlight, temperature swings, and the shape of the terrain. Even on an airless body, there is a kind of slow, thin weather at the molecular level. The far side plays a special role in that new picture. Because it differs in crust thickness, elevation, and temperature structure, it becomes a natural control experiment. You have the same basic inputs: micrometeoroids, solar wind, possible contributions from Earth's atmosphere, but a different environment for those molecules to move through. Comparing near-side and far-side water behaviour lets NASA test models of how volatiles behave on airless worlds in general, not just on this one moon. That matters beyond the moon. The same physics, the same kind of surface migration and cold trapping will apply on Mercury, on some asteroids, and on moons of other planets. If you can understand in detail how water moves and settles on the far side versus the near side, you're building a toolkit to predict where volatiles will hide on any airless body you visit later. And that sets up the next step in the tension. Because once you accept that the moon is quietly moving water and storing space weather in its surface, the question shifts again. How does the whole world behave as a probe sitting in the stream of charged particles from the sun and from Earth's magnetic field, especially on the far side where that interaction plays out differently in the planet's shadow? How do you turn the whole moon into a test instrument for space weather without ever landing anything? One way is to fly spacecraft through the plasma around it over and over and treat the moon as a solid obstacle stuck inside the flow. That's what NASA did when it repurposed two Themis spacecraft into the Artemis mission. Instead of watching Earth's auroras from high orbit, those probes were moved out to the moon and put into orbits that loop around it and pass through the shadow it casts in the solar wind. Around full moon, the moon passes through Earth's magnetotail, the long night-side extension of Earth's magnetic field. In that geometry, the far side is sitting directly in the downstream flow of plasma that's been distorted by our magnetosphere. The moon itself has no global magnetic field and no atmosphere, so the solar wind and magnetotail plasma are free to hit the surface, flow around it, and close behind it. Artemis flies through those regions, measuring particle energies, directions, and electromagnetic fields as the moon blocks and deflects the stream. The key region is the lunar wake, the cavity downstream of the moon in the plasma flow. In simple cartoons, that wake looks like a neat empty cone. Artemis shows it's much messier. The plasma doesn't simply vanish and then refill cleanly. It swirls, it forms boundary layers, and it picks up electric fields as charged particles are removed and replaced. The far-side environment, especially when the moon is in the magnetotail, becomes a natural lab for how plasma deals with a non-magnetic, airless obstacle. The next step is to look at what those measurements say about electric potentials around the moon. Artemis data show that in the wake and near the surface, you can get complex electric fields that set up potentials of tens to hundreds of volts. That means the plasma and the surface are not at the same electrical level. Electrons and ions respond differently, so charges separate, and you end up with pockets where the surface or the nearby plasma is significantly charged relative to the surroundings. That charging is not just a textbook curiosity. Electric fields can accelerate dust grains, lofting them off the surface, especially near terminators where sunlight and shadow meet, or where plasma conditions change quickly. On an airless world, there is no atmosphere to slow that dust down or collapse those fields. If you want to know whether fine grains are going to cling to equipment, float around landers, or get kicked to higher altitudes, you need good measurements of those potentials. Artemis gives that by measuring both the ambient plasma and the fields as it moves through different parts of the wake. Those same fields also affect how charged particles strike and penetrate the regolith. An incoming electron or ion doesn't just fly straight in, its path is bent and moderated by the local electric landscape. Over time, that shapes how radiation damage and implanted particles are distributed with depth and location. When you later drill a core, the pattern of implanted ions and defects is carrying the imprint of billions of passes through different plasma states. Artemis helps decode that by telling you what field structures to expect in different orbital configurations. This leads to a very important clarification. The far side may be radio quiet, but it is not particle quiet. The Moon as a whole lacks a strong global magnetic field, so cosmic rays and solar energetic particles can strike both near-side and far-side surfaces with roughly similar intensity, modulated mainly by direction and by whether the Moon is inside or outside Earth's magnetosphere at a given time. Even when the far side is nicely shielded from Earth's radio noise, it is still sitting in a particle environment shaped by the Sun and the galaxy. The difference between the hemispheres shows up more in the details of exposure geometry than in raw flux. When the Moon is in the magnetotail, the far side sees one pattern of particles, the near side facing Earth can see another. Over millions and billions of years, those differences add up in the regolith. Near-side soils record a mixture of solar wind, magnetotail ions, and some shielding by Earth. Far-side soils, especially at certain latitudes and longitudes, record a slightly different blend, with less direct view of Earth and more time seeing pure solar wind and galactic cosmic rays. From a science point of view, that contrast is useful. If you can bring back matched cores from near-side and far-side sites with similar ages, you can compare isotopes, radiation-damaged tracks, and implanted species. Differences between them help you separate how much of the record comes from the Sun's history, how much from the galaxy's cosmic rays, and how much from Earth's own escaping atmosphere. Artemis gives you the in situ plasma context you need to interpret those differences correctly, instead of guessing. From a human exploration perspective, all of this feeds into a very practical risk calculation. Artemis crews and their hardware will not live in an abstract, average space environment. They will sit in specific field and plasma conditions near the surface. If you know that certain regions of the far side often develop strong electric potentials in the wake, you can predict whether dust is likely to get charged and cling to spacesuits, radiators, and optical surfaces. You can design grounding paths, coatings, and cleaning systems accordingly. The behaviour of fields also matters for electronics. When surfaces and structures charge up to tens or hundreds of volts relative to their surroundings, discharges can occur. On sensitive instruments or power systems, that can cause glitches, false readings, or even damage. Artemis. Data help engineers model how fast charging happens, how fields build up and collapse, and what kinds of shielding or circuit design are needed to keep systems stable over long stays on the far side. Radiation exposure is the other side of the coin. Cosmic rays and solar energetic particles deliver dose deep into materials and tissue. Knowing how often the Moon is in the magnetotail, how the wake structures direct particles, and how regolith responds tells you how deep you need to bury habitats or how thick your shielding needs to be to bring annual dose down to acceptable levels. You don't want to discover after the fact that your safe underground module is shallower than it should be because you misread the particle environment on the far side. So Artemis turns the moon from a passive backdrop into an active probe of plasma physics, electric fields and radiation, exactly in the regime that matters for humans and hardware. It says clearly that the far side is quiet for radio astronomy, but still harsh for particles, and that you have to design around that if you plan to live there. And that raises the next big question for the story. If the plasma and particle environment has been hammering both hemispheres for billions of years, what kind of long-term archive is now buried in the soil itself? And how much of that buried record can tell you not just about the moon, but about Earth's own lost atmospheres and the changing space environment of the inner solar system? If you want to know what the inner solar system has really been doing for billions of years, you need something that's been sitting out there, taking hits and never really resetting. That's what the lunar soil, the regolith, does for you. Every square metre of the moon gets peppered by micrometeoroids and constantly bathed in cosmic rays and charged particles. Each impact and each particle leaves tiny scars, changes isotopes and implants atoms into grains. Over millions and billions of years those signals stack up. On Earth that kind of record gets wiped. You've got atmosphere, oceans, weather, volcanoes, plate tectonics. Rock is recycled, surfaces are buried, melted, eroded. The tape of cosmic ray hits and implanted atoms is constantly overwritten. On the moon, there's no thick atmosphere, no oceans, no plate tectonics. The same basic surface just keeps getting gardened by micrometeoroid impacts, churning the top few meters slowly, but never fully erasing the deeper layers. In a core sample, depth is roughly equal to time. Older layers sit below younger ones, still carrying the damaged tracks and isotopic changes from the environment they formed in. Now add another twist. It's not just the Sun and the galaxy writing data into that tape. Recent work that combines Apollo samples with models of plasma flow shows that part of Earth's own atmosphere has been landing on the moon for a long time. When the moon passes through Earth's magnetotail each month, ions from the upper atmosphere, including oxygen, nitrogen, helium, and even some water-related species, can ride along the magnetic field lines and reach the lunar surface. They embed into grains, especially on the night side where the surface is directly exposed to that flow for days at a time. Estimates suggest this Earth-wind process has been going on for roughly the last 3.5 to 3.7 billion years. That means every time the moon swings through the magnetotail, a tiny bit of Earth's upper atmosphere escapes, travels outward, and some fraction of it slams into lunar soil and stays there. You end up with a mixed record in the regolith, a combination of solar wind ions, galactic cosmic rollers, and a thin component of Earth origin material written into the same grains. The far side matters here because it doesn't see Earth the same way the near side does. The near side is often facing Earth directly, so at certain phases it has a clearer view of outflow from the upper atmosphere and direct plasma interactions. The far side spends more time shielded from that direct outflow by the bulk of the moon, but it still gets hit when the whole system is inside the magnetotail, and it always sees cosmic rays and the background solar wind from directions Earth can't block. That different exposure geometry means far side cores and near side cores won't have identical records. And that's the point. If you drill a core on the near side and a matching one on the far side, and then you compare isotopes like oxygen, nitrogen, and helium, plus radiation damage tracks, the differences tell you how much of the implanted material came from Earth versus the Sun versus galactic cosmic rays. The near side may show stronger signatures of Earth's oxygen and nitrogen in certain layers, while the far side may show a cleaner solar and cosmic ray record, with only a weaker Earth component. Over time, as you go deeper, those patterns also shift. The Sun's activity has changed over billions of years, the strength of the solar wind has evolved, and Earth's magnetic field and atmospheric escape rates have varied. All of that gets integrated into the regolith. If you can date different layers and read their isotopic and damage signatures, you're basically turning the moon into a long-running monitor of space weather and atmospheric loss. This is where the far side becomes especially valuable. Because it is less directly exposed to Earth's outflow and has different plasma conditions, it acts as a kind of control sample. The same processes are in play, but with different geometry. That lets you separate out global signals, like changes in the solar wind and galactic cosmic rays, from local signals tied to Earth's own atmosphere and magnetosphere. Without far-side samples, it's much harder to untangle those contributions cleanly. For future missions, that means far-side drilling is not just about moon geology, it's about Earth's history too. A well-chosen core that goes down several meters could carry a record of how Earth's atmosphere has been leaking into space, how the solar wind has waxed and waned, and how the balance between those sources has shifted. You can't read that record directly on Earth, because Earth erases it. But the moon kept it, in slow, dusty layers. So the stakes are bigger than just understanding the moon better. NASA's measurements and models are turning the far side into an archive of deep time, not only for lunar conditions but for the whole Earth-Moon-Sun system. When you scoop up far-side soil and bring it back to a lab, you're not just reading how often rocks got hit, you're sampling traces of ancient Earth atmospheres, old solar wind states, and long-term cosmic ray fluxes that our own planet has no memory of anymore. That shifts the way you look at those bright, rough highlands on the hidden face. They're not just old crust and craters, they're a storage medium. They've been quietly recording the environment of the inner solar system for billions of years, in a format we're only just starting to decode. And that naturally pushes you to the next point in the story. If the far side is colder, thicker, and holding this deep time archive, how far does that temperature difference go? And what does it do to everything from rock strength to how water and other volatiles behave over the long haul? You've seen that the far side is thicker and less volcanic, so the next question is simple. Is it actually colder? Not just in the shadows, but as a whole system. NASA's Lunar Reconnaissance Orbiter has a key instrument for that called Diviner. It measures infrared radiation from about 0.3 to 400 micrometers, which basically means it takes the moon's temperature, day and night, pass after pass. Over time, it built global temperature maps for every kind of terrain, including the far side highlands. Those maps show a clear pattern. Basaltic Maria, the dark lava plains mostly on the near side, soak up heat in the day and hold onto it longer at night. Highland regions, which dominate the far side, cool faster after sunset and drop to lower minimum temperatures. Same sun, same lack of atmosphere, but different rock and different structure give different thermal behaviour. You can see this in Diviner's data as cooler nighttime curves over highlands, warmer ones over Maria. The far side, with so much highland terrain, spends more of each lunar night at lower surface temperatures than the Maria heavy near side. Surface temperature is only one layer. The next step is to ask, is the interior feeding less heat up to that surface as well? That's where the Chang'e 6 far side samples come in. Lab work on those basalts suggests they crystallized around 2.8 billion years ago, and when you use their chemistry to back out the melt conditions, you get source magma temperatures of roughly 1,100 degrees Celsius, around 2,000 degrees Fahrenheit, about 100 degrees Celsius cooler than comparable age near-side basalts. That lines up with the earlier picture from GRAIL and gamma-ray mapping, less thorium and other heat-producing elements on the far side, thicker crust, and a mantle that simply didn't get or stay as hot. Put that together, and you get a far side that's been thermally more dead for a long time. Thicker crust acts like insulation but also a barrier. Fewer internal heaters mean the mantle under that crust doesn't reach the same melt fractions as the near side. When you combine cooler mantle, thicker lid, and Diviner's cooler nighttime surfaces, you get a consistent story. The far side's thermostat has been set lower, both inside and out, for billions of years. That temperature gap isn't just a number in a table, it changes how almost everything else plays out. Start with rocks and regolith. Colder rocks expand and contract less with the day-night cycle, so you expect less thermal cracking in some far-side terrains. That can change grain sizes, the rate at which bedrock breaks down, and how thick and fluffy the regolith becomes over time. Different thermal stresses mean different mechanical properties. A drill or a rover wheel might see a different response in far-side highlands than in a near-side mare, even if the chemistry is similar. Then look at volatiles. Water and other gases respond strongly to temperature. Colder regions are better at trapping and holding on to them. If far-side polar zones routinely run a bit colder or have colder subsurface conditions, they can act as more efficient cold traps. A water molecule hopping across the surface is more likely to stick when it hits those areas and stay there longer. That affects where ice builds up, how thick deposits can get, and how long they can survive during periods of higher solar activity. Magma is affected too. Cooler crust and mantle resist intrusions. Even if you have a pocket of melt at depth, pushing it through 50 to 60 kilometers of cooler, stronger rock is harder than pushing it through 30 to 40 kilometers of warmer, weaker rock. That's one reason why big far-side basins don't show the same kind of wide, dark mare floods that you see on the near side. The impacts were there, the basins are there, but the temperature and thickness profiles stack the deck against large-scale lava eruptions. All of this feeds into mission design. If you're planning to put heat flow probes into the ground to measure internal heat loss, you expect different numbers on the far side and the near side, because the underlying engine strength is different. If you're designing drilling hardware or anchoring systems for habitats, colder, possibly stronger crust can change how much force you need and how hardware will fatigue over time. Even simple things like how fast buried cables or pipes equilibrate with the background matter more when one hemisphere is cooler at depth. The big picture here is that the Moon does not have one global temperature history or one global thermal structure. For a long time, models assumed one magma ocean, one cooling curve, minor variations. NASA's thermal maps from Diviner, plus far-side sample data and the distribution of heat-producing elements, show that isn't true. The near side followed a warmer, more volcanic path for longer. The far side set into a colder, less active state earlier, and has stayed that way. That forces modelers to treat each hemisphere almost like a separate thermal experiment. Same starting conditions in broad strokes, but different internal heating, different crust thickness, different cooling rates and different outcomes. When they try to reconstruct the Moon's evolution, they can't just fit one curve to all the data. They have to ask, what did the near side do through time, and what did the far side do, and how did the two influence each other? And once you accept that the Moon's thermostat isn't uniform, the last big question in this arc becomes even more pressing. If one side is thicker, cooler and less volcanic, but preserving more impact scars and more ancient signatures, how does that change the way we use those far-side craters to time the earliest, most violent phase of the solar system, and to pin down when it finally got quiet enough for places like Earth to hold stable oceans and early life? If you want to know how old a surface is on an airless world, you don't look for trees or erosion, you look at craters. The basic rule is simple. More craters usually means an older surface. Every impact leaves a scar. Over time, new craters land on top of old ones. On the far side highlands of the Moon, that process has gone on almost to the limit. The terrain is so packed with craters that in many areas, small ones overlap bigger ones until they're almost erased. When you zoom in on high-resolution images, there are barely any clean, flat patches left. That tells you those regions have been exposed for a very long time, pretty much since the Moon's crust solidified. But crater counting is more than just, this area looks older than that one. Scientists actually build size-frequency distributions. They count how many craters of a given diameter exist per square kilometre, and they do that across multiple size ranges. Those curves can then be compared between regions. If two surfaces were exposed to the same impact environment for different amounts of time, the older one will have more craters at all sizes. If the curves differ in shape, you might be looking at changes in the impactor population over time. To turn that relative method into absolute ages, you need anchor points, surfaces where you know both the crater statistics and the actual age from samples or solid modelling. On the far side, one of the most important anchors is the South Pole Aitken basin, SPA. Its formation age, based on dating minerals linked to it, sits around 4.2 to 4.34 billion years. That makes it one of the oldest recognisable impact features in the whole solar system. Once you have that age, you can look at how many craters per square kilometre have accumulated on SPA's floor and rim since it formed. That gives you a measure of the average impact rate over that early window. Then you can go to another far side terrain, count its craters, and ask it how many of these must have formed after SPA. By matching the curves, you can estimate how much younger or older that terrain is compared to the SPA reference. This is especially powerful on the far side because there are so many old highland regions that never got resurfaced by big lava flows. The crater record there is closer to continuous. With high-resolution LRO imagery, you can count down to smaller crater sizes with good confidence. That tightens the statistics and helps refine models of how the bombardment rate dropped over time from the early violent phase to the quieter, more recent state. Now compare that to what you see on the near side. Dark mare basalts flooded many basins there, wiping out older craters and resetting the clock on those surfaces. The nearside Maria formed in multiple episodes, mostly between about 3.9 and 3.1 billion years ago, with some younger flows. Their crater densities reflect both the time of their emplacement and any later impacts. On the far side, volcanic plains are rare, but they do exist in a few basins and low areas. When you compare crater statistics on those rare far side plains to similar-looking nearside Maria, you find subtle but real differences. Some far side plains have crater densities that suggest they formed at slightly different times than you would expect if all Maria everywhere erupted in the same global episodes. Others hint at a different mix of impactors, meaning the population of objects hitting the Moon may have evolved in ways that vary with time, and maybe with orbital dynamics. Those shifts might sound small, but they feed back into the broader timeline of the inner solar system calming down. If far-side plains show that certain areas stayed volcanically or impact-wise active longer or shorter than the near side, you have to adjust your curves for the heavy bombardment era and its tail, and because the Moon and Earth share that impact environment, those adjustments apply to Earth's early surface conditions too. This is where the stakes jump from moon geology to when could life actually hang on at the surface of Earth without being wiped out repeatedly. Early on, impacts large enough to create basins like SPA would have delivered so much energy that any shallow oceans on Earth could have been vaporized, and any surface life would be under heavy stress or wiped out. As the impact rate dropped, there would have been a transition period when the hits were still frequent, but not globally catastrophic, and then a stage when truly sterilizing events became very rare. By tightening ages on far-side surfaces, especially very old highlands and plains with well-defined crater statistics, you refine that transition. You get better constraints on when the impact rate dropped by factors of 10, 100, and so on. That feeds into models for when Earth's oceans could stay stable for long stretches, when early crust could survive without being totally recycled, and when surface or near-surface life would have had a real chance to establish and persist. In other words, every time someone counts craters on a far-side highland tile from LRO's map, they're indirectly updating the story of when Earth stopped being a shooting gallery hostile to persistent life and started being a place where you could keep oceans and ecosystems going for hundreds of millions of years at a time. The Hidden Hemisphere's crater record is not just a catalogue of impacts on the Moon, it is a timing tool for the entire early inner solar system. And once you realise the far side is giving you that kind of leverage on deep time, you run into a very immediate problem. How do you explore and use that hemisphere in the Artemis era without trampling the very records, ice deposits, and radio quiet zones that make it scientifically unique in the first place? How do you build bases, mines, and observatories on the same hidden hemisphere without wrecking the very things that make it special? That's the problem Artemis runs straight into. NASA's current plan is to land crews near the lunar South Pole in the late 2020s and 2030s, and a lot of those candidate landing zones sit right on the edge between the near side and the far side. The logic is clear. You want to be close to permanently shadowed regions that may hold ice, but you also want line of sight to Earth for direct radio contact. So the first bases hug the limb, where a small change in location pushes you farther onto the far side. Once you put people, power and hardware there, the next step is obvious. Infrastructure creeps. You run power cables a bit farther, you send rovers over the ridge, You drop relay satellites in orbits that can see deeper into far-side territory. Over a couple of decades, it's easy to go from we're just working at the edge to we have permanent operations well over the limb, unless you actively decide to limit that spread. Scientists are looking at that drift and saying, we need to mark out the most valuable science sites now, before that happens. You'll see the phrase sites of extraordinary scientific importance, or similar language, in papers and proposals. The idea is to legally and operationally protect specific areas on the far side and near the poles, both PSRs that hold ancient ice and radio-quiet zones that are prime for low-frequency astronomy and other ultra-sensitive instruments. Those sites are not just nice to have. Some PSRs are the best places to drill pristine ice cores that record billions of years of volatile delivery. Some far-side basins and plateaus are the only spots quiet enough for huge low-frequency radio arrays, or even future gravitational wave detectors sitting on a stable, airless surface. If you contaminate those locations with radio noise, exhaust plumes, or big thermal disturbances, you lose once per solar system opportunities. The catch is, the same physical properties that make these places scientifically perfect also make them attractive for operations. A permanently shadowed crater floor is incredibly cold and radio quiet, great for a radio array or a gravity experiment, but that same crater might be rich in accessible ice, exactly what you want to mine for water and fuel. A far-side plateau with clear views of the sky is ideal for astronomy, but it's also a good place to put solar panels, communication relays, and maybe even a logistics hub. That's the tension Artemis planners and international partners are starting to talk about directly. You can't pretend it's not there. NASA documents and community reports increasingly use words like coexistence. That means thinking hard about questions like, can you run a mining operation near a protected science zone without flooding it with dust and radio noise? Can you time high-power transmissions to avoid key observing windows? Can you route traffic around certain crater rims instead of over them, even if it's less convenient? For commercial operators, this isn't just an ethical issue, it's a regulatory one waiting to happen. If certain far-side sites get protected under international agreements, you won't be allowed to just drop a lander wherever you want, at whatever frequency you want. There will be quiet zones, buffer zones, maybe even no-go areas for heavy industry. That kind of framework doesn't exist in detail yet, but you can see the pressure building as more countries and companies talk about lunar mining and long-term habitats. So the far side is about to become a test case. Do we treat it as a shared scientific asset with strict protection in key areas? Or as open territory where we fix problems later, after damage is done? The answer matters far beyond the moon. However we handle these far-side PSRs and radio-quiet basins will set precedents for Mars polar caps, for icy moons like Europa and Enceladus, and for resource-rich asteroids. If we show we can balance extraction, habitation, and pure science on the moon, we have a playbook for everywhere else. If we fail, we carry that failure forward too. And that leads directly into your final question for this whole story arc. After everything NASA and its partners have found on the hidden hemisphere, what does the dark side of the moon really mean now? And how does that two-faced, lopsided world force us to rewrite not just the moon's origin story, but the way we think about other moons and planets orbiting other stars? So what does dark side of the moon really mean now, after everything you've just seen? When you put all the pieces together, the far side is not just the half we don't see, it's a completely different beast. Its crust is thicker by roughly 20 kilometers, about 12 miles. Its mantle runs cooler, it barely has any mare seas at all. Its gravity field has different Mascon patterns. It hosts rare, one-off silicic volcanoes like Compton Belkovich, and it carries radio-silent, ice-rich polar environments that the near side simply doesn't have. That stack of asymmetries does not fit the old picture of a small, uniform, boring moon that just froze and sat there. Think through that list for a second. Thicker far-side crust from the GRAIL gravity map. Colder source magmas from Chang'e 6. Almost no big dark basalt seas when you flip the global images over. Gravity anomalies that don't match the near side pattern. a lone silicic volcanic complex in the wrong hemisphere, plus the quietest radio zone and some of the coldest ice traps in the inner solar system. If you drew that up as a theoretical example for students and said, "Design me a simple symmetric formation model that produces this," they'd tell you it's over-constrained, it won't fit. The moon is forcing that same answer on the real models, so the next question is brutal. What kind of formation stories are still allowed? Any serious model for how the moon formed and cooled now has to explain in detail why heat-producing elements like thorium and uranium ended up pooled mostly on the near side, why the crust thickened so much more on the far side, and why volcanism was so one-sided and stayed that way for billions of years. You can't hand-wave it as just random variation when the signal is this strong and this global. One class of ideas says the original giant impact that created the moon was off-center. In that picture, when a Mars-sized body hit early Earth, the debris disk and the resulting magma ocean didn't spread heat and elements evenly. More of the radioactive hot stuff and more of the early melt ended up on one hemisphere, the side that became the near side. That would naturally make that hemisphere thinner, hotter, and more volcanic. Another idea focuses on the crystallization of a global magma ocean. As that ocean cooled, different minerals would have crystallized and sunk or floated at different stages. If that process was even slightly asymmetric, you could end up with a thicker crust piling up on one half and a more melt-rich, element-rich mantle domain under the other half. Over time, that would turn into a near side that keeps erupting basalt and a far side that shuts down faster. Then there's the more radical proposal, an early collision between the young moon and a smaller companion moon. In that scenario, you first form two moons from the giant impact debris in nearby orbits. Later, the smaller one collides gently with the larger one and splats onto one hemisphere, adding extra crustal material and changing the thickness and composition profile in a single hemisphere scale event. That would literally plaster one side with extra rock and could help explain why the far side is so much thicker and more highland dominated. The key point is, none of these models can ignore the far side anymore. You can't tune them to match just the Maria ages on the near side or just the average crust thickness. You have to match the whole asymmetry, crust, heat sources, volcanism, history, gravity field, thermal evolution, the lot. NASA's data and partner missions like Chang'e 6 turned the far side from an optional detail into a make-or-break test. If your formation model can't reproduce a two-faced moon, it's not done. Now step back one level and ask, why does this matter beyond our own backyard? Because the same physics that made our moon lopsided is going to show up all over the galaxy. Tidal locking, where one side always faces the parent planet, is common. Crustal asymmetry, where one hemisphere loses heat differently or gets more radioactive elements, is likely on many moons and close-in rocky exoplanets. One-sided volcanism, where one face is resurfaced and the other keeps its scars, is going to be a recurring pattern, not a one-off. When we eventually get detailed data on exomoons orbiting gas giants, or on rocky worlds hugging close to their stars, we won't see them in person first. We'll see light curves, spectra, maybe rough maps from future telescopes. If one side has different thermal emission, different volcanic gas signatures, or different reflectivity than the other, the toolkit we built on the moon becomes the decoder ring. We'll ask the same questions. Is the crust thicker on one side? Do heat-producing elements pool? Is volcanism asymmetric? Is one hemisphere storing ancient scars while the other is resurfaced? By decoding our own two-faced moon with real hard data, we're training ourselves to read those distant worlds when they finally come into focus. The moon stops being just the thing we went to in the 1960s and turns into the first case study of a tidal-locked, geologically lopsided body that we can touch, drill, and orbit with absurd precision. That case study then gets exported to exoplanet science, to mission design around other stars, to how we think about habitability on worlds that always show the same face to their suns. So when you drop Dark Side of the Moon in your video title, you're not talking about a spooky blank hemisphere that nobody has seen. You're pointing at the half that turned out to be more extreme, more informative, and honestly more alien than the face that fills our sky. The far side has the deepest impact basin, the thickest crust, the oldest crater record, the coldest traps, the quietest radio zone, and one of the strangest volcanic complexes in the whole inner solar system. It's the side that refused to fit the easy story. The hidden hemisphere didn't just complete the picture, it broke it. It forced everyone to redraw it. It took the moon from a simple dead rock idea to a layered archive of deep time, where every asymmetry tells you something about violent impacts, uneven cooling, shifting water, escaping atmospheres, and even the early history of Earth itself. When astronauts finally stand on that far side in the Artemis era and beyond, they won't just be going to the back, they'll be standing inside the best, most accessible time capsule for how rocky worlds are built and beaten up here and across the galaxy. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.